All right, welcome to the 32nd International Conference on Formal Power Series and Algebraic Combinatorics, also known as FIPSAC. My name is Sean Griffin, and today we have 3 speakers. Just as always, each talk is 25 minutes long with 5 minutes in between for questions and a short break. And there will be a coffee break at the end of the session if you want to stick around for that. Everyone is welcome to participate. And today's chat monitor for today is Sheila Sundaram. And let me introduce the first speaker, which is Spencer Backman. He'll be talking about simplicial generation of Chow rings as matroids. Take it away.
Great, thanks so much. Okay, so this is joint work with Chris Aywer and Connor Simpson. I'll just jump in. Okay, so we'll try to start at the very beginning. So a matroid is a finite combinatorial structure with many different axiom systems, which all wind up being miraculously equivalent. Rota popularized the terminology cryptomorphic to say that all of these things are equivalent, but not obviously equivalent. So perhaps the most fundamental definition is in terms of independent sets. So the matroid will be defined on some ground set E, and we'll say that I is the collection of independent sets of a matroid if it satisfies the following 3 axioms. So the first is just that I is non-empty, and the second is that this collection of sets is downward closed. So the first and second axiom just say that you can think of the collection of independent sets as an abstract simplicial complex, if you prefer. And then the third axiom, which is really the heart of the matroid theory, is saying that if you have 2 independent sets, cardinality of one is larger than the cardinality of the other, then you can throw in some element from the bigger set into the smaller set to get another independent set. So for example, if you have that E is just a collection of vectors from some vector space, then the collection of all independent sets of vectors, linearly independent sets of vectors, will form the independent sets of a matroid. But matroids are much more general, so asymptotically, almost all matroids are not coming from vector configurations. Okay, so now that we have the notion of the independent sets of a matroid, we'll define what the rank of a subset of E is going to be. So this is just the maximum size of an independent set contained in the set X. And so you can think about this as being the dimension of the span of a collection of vectors. So this rank function is monotonic. If X is contained in Y, then the rank of X is less than the rank of Y. And then the really interesting one is the submodularity property. So the rank of X union Y plus the rank of X intersect Y is at most the rank of X plus the rank of Y. And you can work out that this actually gives a different axiom system for matroids if I say one other thing. So Edmonds was the first person to say that we can think about matroids from the perspective of polyhedral geometry. So if we fix some non-negative monotonic submodular function f, then we can associate a certain polytope called a polymatroid base polytope. So what we do is we say for a collection of indices contained in this set E, the sum of the entries from those indices corresponding to those indices should be at most FA. And then this one extra linear condition, which is that the sum of the xi, where I ranges over all of the indices, is just going to be equal to this number Fe. So if we add this one extra constraint that f of x is at most the cardinality of x, then we get what are called the matroid base polytopes. So that's where the sort of poly prefix in polymatroid comes from, is that we don't insist that this function f of x is bounded from above by x. Okay, that took 4 minutes to say. Okay, so Postnikov defined a generalized Permita to be a polytope whose normal fan is the coarsening of the braid arrangement. So, you know, this is called a generalized permutahedron because it generalizes the permutahedron. The permutahedron, its normal fan is the braid arrangement.
Can I
And
just
then we're
quickly
just
interrupt? Spencer,
Yeah.
Art Duval said, what's F subscript A?
Right. So F sub A, this is a function, right? I didn't define the domain or the range. F is a function from this ground set E, excuse me, from the, yeah, it's a function from the power set of E to the real numbers. And so since A is some subset of E, F sub A is the function defined on A. Thank you. Yeah, the notation was not sufficient.
Thank you.
Is that clear? Hopefully it is. Yeah. Okay, so generalized permutahedron is a polytope, like I was saying, whose normal fan is a coarsening of the braid arrangement. So generalizes permutahedron. And then there's this sort of folklore theorem, which says that up to translation, the set of generalized permutahedra is the same thing as the set of polymatroid-based polytopes. And so I'll make this side remark that this perspective is compatible with this idea of Galfond and others, that matroids are really a type A structure, which is generalized by Coxeter, by the notion of a Coxeter matroid. And it's not the point of my talk, but I figured that considering the audience, it would be an appropriate remark to make. And also just to say that I think that there tends to be a general feeling that these are coming back into the limelight. So for people in the audience who may be interested in Coxeter groups, but know less about matroids, you know, maybe team up with a matroid theorist and prove some things. Okay, so here's a simple observation, is that standard simplices are generalized permutahedra. So if you look at the normal fan of a standard simplex, this is going to be some coarsening of the braid arrangement. So here I have a picture of a triangle sitting inside of the braid arrangement associated to A3. And you can see that its normal fan is going to be a coarsening of the braid arrangement. Here's another simple observation. So generalized permutahedra are closed under Minkowski summation. So if you don't know what Minkowski summation is, this is just, if you take two convex bodies, e.g. polytopes, you can look at their pointwise sum. So it's the collection of all pairs, excuse me, the collection of all sums of pairs of points. And more generally, we can take the Minkowski sum of a collection of polytopes. And yeah, so generalized permutahedra are closed under this summation operation. In general, if you have the collection of polytopes whose normal fans are the coarsening of a fixed fan, they're going to be closed under Minkowski summation. So classic example of a permutahedron which can be viewed as a generalized permutahedron which can be viewed as a Minkowski sum of standard simplices is the permutahedron. So the permutahedron is going to be the sum of all of the line segments connecting EI to EJ. So here I've shown the hexagon is the sum of these three line segments. So Postnikov really advocated in his seminal paper, what's it called, Permutahedra, Associahedra, and Beyond, that you can look at this cone generated by Minkowski sums of standard simplices, and this forms a pretty special subcone of the cone of all generalized permutahedra. And sort of, if you want just like a one-line idea of what my talk is about today, it's introducing a matroidal extension of this philosophy. Okay, so another important object associated to a matroid is the notion of a flat. So if you have your matroid and you take some subset of the ground set, we'll say that it's a flat if adding any element to it causes the rank to increase. So in terms of, if you want to think about vector configurations, the flats correspond to the spans of the subsets of the vectors. They're sort of the closed sets in matroid theory. So this set of flats forms a lattice, which is not hard to prove. And we'll denote that for the rest of the talk by math cal L of M. Okay, so another object of interest in this talk is the Bergman fan of a matroid. So the Bergman fan is a certain polyhedral fan which is obtained as the fan over the order complex of the lattice of flats. So if you don't recall what an order complex is, this is just the idea that for every chain of flats, we're going to get a face. So the rays correspond to the flats, and then a collection of rays spans a cone if they form a chain in the lattice. So where this was coming from, like the motivation of this is that is really from tropical geometry. So the one line I'll say about tropical geometry in this talk is that in the case of matroids which come from vector configurations, equivalently linear spaces, a Bergman fan is set theoretically the tropicalization of a linear space. And so this definition of Ardila and Clivens extends that notion to all matroids. And they prove that it has this particularly nice unimodular triangulation. So here I've drawn the Bergman fan of what's called U23, which is the matroid associated to 3 generic vectors in the plane. So some comments about how the Bergman fans relate to the braid arrangement. So the braid arrangement is itself actually a Bergman fan. So if I take a collection of linearly independent vectors, that defines a matroid. And the independent sets are just the set of all subsets, because if you take a collection of linearly independent vectors, then every subset is obviously linearly independent. So that's called sometimes the free matroid. And if you think about the lattice of flats there, the lattice of flats is just the Boolean lattice. And so the Bergman fan you're going to obtain is going to be exactly the braid arrangement. Moreover, every Bergman fan is a subfan of the braid arrangement. And this is just coming from the fact that it's the fan over an order complex. I mean, Bergman fans are more special than that, but simply because, for that reason, you can see them as living inside of the braid arrangement. Okay, the next object of this talk is the Chow ring of a matroid. So this was essentially introduced by Feichner and Usvinsky. If you want a compact description, you say that, okay, well, the Bergman fan is a rational polyhedral fan. In fact, it's smooth and simplicial. And so every rational fan has a toric variety associated to that. And you can look at the Chow cohomology ring of the toric variety of this Bergman fan, and that is some ring A star of M. Okay, but we're combinatorialists. It would be nice if there were something more concrete that we could look at. So the general theory of toric varieties tells us that the Chow ring of this Bergman fan has the following description. So we'll start off with just this polynomial ring whose variables are going to be indexed by the non-empty flats of the matroid. And we're going to quotient out by 2 different ideals. The first one, I, is just going to be a collection of quadratic monomials. So we'll have all pairs x sub f and x sub g, where f and g are incomparable flats. So this is actually just the Stanley-Reisner ideal of the Bergman fan. So the point is that when this is a flag complex, if you want to think about it that way. So we have this collection of pairs of variables, and when we quotient out by them, everything that's left over is just going to correspond to a chain of flats. So basically, quotienting out by I kills everything except for monomials, which correspond to a chain of flats. And then the second ideal is going to be this ideal J, which is a collection of linear forms. So for every element of the ground set E, we get a linear form, which is the sum of all of the variables corresponding to flats which contain that element. So what to say there. So I, you should think of as encoding the combinatorics of the Bergman fan, and J is encoding the geometry. So if this were, say, the braid arrangement, then J is essentially telling you that you care about functions up to translation. There's a basis for the collection of global linear functions on your fan. And for people who think about Stanley-Reisner rings, I think an important remark here is that this is not a linear system of parameters. So the number of linear forms here is equal to the cardinality of the ground set, but that is strictly larger, almost always, than the rank of the matroid. So the dimension of the Bergman fan is the rank of the matroid, and the collection of linear forms is the cardinality of the ground set. So we have, it's a bit of magic that in the end, this winds up being an Artinian ring, which is not the zero ring. So for Stanley-Reisner specialists, they might note that that's somewhat unexpected. So the first indication that there's something important going on here. Okay, I should probably speed up a little bit. Okay, so in 2015, I think, Karim Adiprasito, Junha, and Eric Katz announced this proof of the Heron Rota Welsh conjecture for matroids, which had been open for about 45 years. And they settled this conjecture by developing a Hodge theory for matroids, a certain synthetic Hodge theory for matroids. So what they proved, and I'm not going to formally state these things, but they proved that the Chow ring has a Kähler package, that is, it satisfies Poincaré duality, the Hard-Lefschetz theorem, and the Hodge-Riemann relations. The reason that this is so unexpected is because the toric variety of the Bergman fan is not a projective variety. It is smooth, but it's not projective. It's not even complete. And so there's really no reason to expect that that the cohomology ring would satisfy these properties, yet they do. So both Hard-Lefschetz and the Hodge-Riemann relations are defined in terms of something called the combinatorial ample cone. So if you take a linear form, which is just some linear combination of these variables xf's, the coefficients are from R, we'll say that it's ample if these coefficients satisfy the strict submodularity property. And the Neff cone is going to be the closure of the ample cone. So that's when we drop this condition that the strict submodularity is strict. So the Neff cone is just going to be the cone of submodular functions on the lattice of flats. So when M is the free matroid, so that our Bergman fan is the braid arrangement, the Neff cone is exactly the collection of generalized permutahedra. So if you want to, you can think about this Neff cone as a matroidal extension of the set of generalized permutahedra. But they're no longer polytopes, they're just linear functions. Okay, so I'll go this slide. Yeah, so it's not so important for the rest of the talk, but I wanted to just write down what is the characteristic polynomial. So it is going to be this alternating sum over the subsets of the ground set, where one keeps track essentially of the rank of that ground set. And so this Heron Rota Welsh conjecture was that the coefficients of the characteristic polynomial are log-concave. If you don't know what that means, it's just that if you take the logarithm of the coefficients, you get a concave sequence. So the proof of log-concavity in the end followed from a nice application of these Hodge-Riemann relations in degree 1. Okay, so the proofs of these, and I'll remark that the proofs of this Kähler package, this Poincaré duality, Hard-Lefschetz and Hodge-Riemann relations utilize a certain flipping procedure, which interpolates between the normal fan of a simplex and the Bergman fan of a matroid. And this was inspired by some earlier work of McMullen on the polytope algebra. So this is, yeah, this was the work of Adiprasito, Han, Katz. So now I'm getting to our contribution. So let's define this linear function h sub f, which is just going to be for any particular flat f, we sum up all of the flats that contain f. And there's a minus sign in there, which I'll explain soon. So what are these objects? These are essentially the restriction of the support function of a simplex to the Bergman fan. So the support function of the simplex, you can think of it as being defined on the rays of the braid arrangement. And when you restrict that function to the Bergman fan, this is exactly what you get. So for this reason, we call this change of variables in the presentation of the Chow ring in these variables, the simplicial, which I mentioned earlier, which we promote in our paper, is that the cone generated by these HFs forms a special subcone of the Neff cone of the Chow ring. So yeah, I just want to remark quickly that in fact, this is really the restriction of the support function of the negative simplex. That's why that minus sign is there. It's something you can't see for the braid arrangement because the braid arrangement is essentially symmetric. But when we're working with Bergman fans, we need to keep track of this. So it's just a technical detail. So as an application of our presentation, we're able to give a new proof of the Hodge-Riemann relations in degree 1, which in turn, as I've mentioned, implies the log-concavity of the characteristic polynomial. And our proof avoids this flipping technique, which was central to the Adiprasito-Katz proof. So some comments about what these HFs are doing. So we'll say that a matroid M prime is a quotient of M if its lattice of flats is contained in the lattice of flats of M. So there's a special type, this is a classical part of matroid theory. And in particular, given a flat in F, we can associate something called a principal truncation. So this is a quotient of M which has rank 1 less. So one of the main theorems of our paper is that we prove that multiplication by HF in this Chow ring precisely corresponds to a principal truncation. So the idea is that these new variables that we're working with are encoding the theory of principal truncations of a matroid. And we're able to apply this to give a vector space basis for our Chow ring in terms of the relative Schubert matroids. So this generalizes a result of Hampa, who showed that the Bergman fans of Schubert matroids give a basis for the Chow ring of the braid arrangement. And furthermore, we apply this to recover Poincaré duality. Okay, so I mentioned that Postnikov had this theory about Minkowski sums of standard simplices as forming a special cone inside of the cone of generalized Permita-Hydra. But he really did a lot more than that. He proved a bunch of really interesting things about this cone. And in particular, he used this cone to calculate the volumes of arbitrary generalized Permita-Hydra. And the result that he introduced there for doing this was what's called the dragon marriage theorem. So I'm not going to state the dragon marriage theorem, but I'll state our matroidal generalization, which we call the Dragon-Hall-Rota theorem. So let's let H sub F1 through H sub Fd be a collection of D simplicial generators, where D is, I haven't written this, but it's going to be 1 less than the rank of the matroid. So the product of these HFs is actually going to correspond to a real number. So in general, every monomial in this Chow ring corresponds to a real number. And we prove that this product of the HFs is always either going to be 0 or 1, and we give a precise condition on when it's going to be 1. So in particular, what we need is that the rank of the union of these flats is going to be at least the cardinality of the collection of indices plus 1, and it's 0 otherwise. So this is like a generalization of a mixed volume computation for the braid arrangement. So I'll remark that at FIPSAC 2019, Ayur described a closed form for intersection numbers in the classical presentation of the Chow ring in terms of flag Mobius numbers. And actually at the time of writing, we know that these must be equivalent, but we do not have a proof. I think I'm coming close to the end. So let me say that the volume polynomial is just a certain polynomial associated to linear forms. And we utilize our Dragon-Hall-Rotto theorem and Brandon Hu's theory of Lorentzian polynomials to prove that the volume polynomial for the simplicial presentation of the Chow ring is log-concave in the positive orthant. And as an application of this, we apply induction and this Hopf theoretic structure on the lattice of flats to prove, to recover the Hodge-Riemann relations in degree 1, which themselves imply the log-concavity of the characteristic polynomial. And that's the end of my talk. Thank you.
So Spencer, if you can stop sharing so we can thank you properly.
Okay. Stop.
So you can press the reaction button and stop. And I'll turn it over to Sheila for questions. We have about 4 or 5 minutes.
Thank you for a very nice talk. Let's see, there was a little bit of discussion about whether the Chow ring was finite dimensional between Dari and some other people, but whether Artinian was equivalent to being finite dimensional.
I mean, it's like being the coordinate ring. I mean, I guess I want to say that it's 0-dimensional. I mean, isn't Artinian the same as 0-dimensional?
Sorry, I meant vector space dimension, not Krull.
Oh, vector space dimensional. So this is a graded, right? It's a graded Artinian ring, and the highest degree of a monomial is going to be the rank of the matroid -1, and each graded piece we give a vector space basis in terms of monomials associated to what we call relative Schubert matroids, loopless relative Schubert matroids. So we know what the Hilbert series is, if that's what you're asking.
Okay. Well, anyway, if you speak of a Poincaré duality, it better be finite dimensional.
Yes, it is finite dimensional, and I mean we know explicitly what the dimensions.
Thank you. And Dari also asked in your definition of an ample cone, if you want F and G not to include each other, so that you get straight.
Yeah, so that's a very reasonable question. So I mean, in general, when one talks about matroids or polymatroids, you have this non-negativity, the monotonicity, and the submodularity. But here, because of the linear forms, we can get away with only caring about submodularity. So you can add some positive combination of these linear forms to make sure that it's always non-negative and monotonic, I believe.
Thank you. And then Jake Levinson says, for representable matroids, does that relative Schubert matroid statement you gave correspond to some kind of stratification of the matroid variety?
Yeah, so the point is that in the case of realizable or representable matroids, there is a Chow equivalence between the Chow ring of a matroid and the cohomology ring of the wonderful compactification of a hyperplane complement, hyperplane arrangement complement. And our variables HFs have some particular meaning there. And so you can interpret these relative Schubert matroids as certain classes there, which I think you can think of as having a certain flag interpretation. So yeah, I would just refer you to our paper if you want to see more about that.
I don't see, oh, here's another question. Alejandro asked if the Lorentzian property comes from being a volume polynomial of polytopes.
No, so that's a very good question. There are no polytopes anymore. What it's morally speaking, it's coming from the fact that we're working with these Neff classes, but the Neff classes are just combinatorial Neff classes. There are no, I mean, there are no ample divisors anymore because this is not a projective variety. But the idea is that for some reason, because matroids are magic or whatever, these combinatorial Neff classes behave as if they were actual Neff classes. But I mean, it requires a combinatorial proof that this thing is log-concave. I think actually in the realizable case, you can get away with using this wonderful compactification to prove it directly.
All right, so it looks like there's one more question in chat, but let's move the rest of the questions to Slack. Let's thank Spencer again for his great talk.